right, before I go ahead and do the peptide bonds, like I promised you, I will get to that, and it's later on the what you need to know list. Let's get into the acid-base properties of amino acids. Now, we already know that an amino acid, just from the name, has an amino group and an acid group. The acid group behaves as an acid. It likes to donate a proton. It likes to get deprotonated. The amino group behaves as a base. It likes to add a proton. It likes to get protonated. Um, so the fact that we already drew it as a Zwitter ion shows that we understand that idea, that the acid group loses a proton and the base adds a proton. Now, when you take that Zwitter ion and you move it to a very low pH, it gets very affected by the environment. So if you remember, low pH means a very, very high concentration of hydrogen ions. So if you're bombarding the amino acid with a lot of hydrogen ions in solution, then the amino acid starts to pick up any hydrogen ions it can. So let me show you what I mean. Let's just draw a simple glycine. So here's glycine drawn as a Zwitter ion. Okay, so this is the side chain. So here's my glycine, all right? Now, let's say this is at a pH of 7. When the carboxylic acid group, the carboxyl, becomes a carboxylate ion, and the amino group becomes an ammonium ion. Now, if I take this down to, oh gosh, come on. If I take this down to a very low pH, like 2 or 1, very low pH. So now let's say I'm at a pH of 1, super low pH. What does that mean? It means you have a very high concentration of hydrogen ions or very high concentration of hydronium ions. Tons and tons and tons of hydrogen ions at this very low pH. So anything that can pick up a hydrogen ion is going to. Well, who can pick it up? This guy can. So at a pH of 1, this carboxylate ion picks up a hydrogen ion. It gets protonated. And nothing else can get protonated. That's the only place that can pick one up. And there you've got glycine at a pH of 1, pH 1, 2. Anything very low pH, this is what it's going to look like. Okay? Now let's say I'm at a very high pH. Let's say pH 12 or pH 13, super high pH, very basic. Think lots and lots and lots of, imagine lots of hydroxide ions, okay? So in order to relieve the stress of all those hydroxide ions, one of the hydrogen ions in this is going to leave and try to neutralize the hydroxide to make it water. Think of it that way. So at a super high pH, so this is at pH 1, but this is pH 7. So now we're going to go to pH 12 or 13. So pH 13, very high pH, super high pH. What's going to happen? Think lots of hydroxide ions, lots and lots and lots. So you want to neutralize all of this. So anything that can neutralize it by, if you can have a hydrogen ion leave this and neutralize it and make it into water, it's going to do that at a high pH. So when we redraw it at a high pH, our glycine, what hydrogen can go? This one over here. This can get deprotonated. So this gets deprotonated and you end up with this. So at a super high pH, glycine's going to look like this. Notice it has a -1 charge. Let's redraw the one that we had earlier at a very low pH. This is glycine at a super low pH. Go. What does glycine look like at a super low pH? pH 1, like this. So it's going to have a positive 1 charge. And this is going to be the case for all amino acids. All amino acids at a very low pH are going to get protonated. So any carboxylate ion stops being a carboxylate ion at a low pH. It picks up a proton, has no charge. At a very high pH, all amino acids, all the ammonium ions, stop being ammonium ions and they become aminos again. It's just plain old simple amine without a charge. All right? So at low pHs, all the carboxylate ions become protonated. So at low pH, basically when everything is acidic, super acidic, all carboxylate ions become protonated, meaning they pick up a proton and then they don't have a charge anymore and have no charge. Okay, that's the scenario at low pH. At high pH, so the carboxylate ions are all the acidic sites. All the acidic sites get protonated. At a high pH, all the ammonium ions, which are all the basic sites, these are all the acidic sites, and these are going to be called the basic sites. The basic sites are all the ammonium ions. At high pH, all the ammonium ions become deprotonated. Deprotonated, and they have no charge. At a neutral pH, at a pH of 7, the acidic sites are deprotonated and the ammonium sites are protonated. So basically at a pH of 7, it's the way we've been drawing the Zwitter ions. But for this class, we're just going to think extremes. We're going to think at a very low pH, this is what happens. At a very high pH, this is what happens. And at a pH of 7, we'll just draw them the way we did all the Zwitter ions before. Okay? So just for practice, let me show you an aspartic acid at all 3 pHs. Okay? So if I've got aspartic acid, let me do this. Aspartic acid at a pH of 1. And then I'm going to draw aspartic acid at a pH of 7. And then I'll draw aspartic acid at a pH of, let's say, 13, super high pH. Okay, at a pH of 1, remember we said all the acidic sites are protonated. See, I'm drawing it the way I've always drawn these things. It's hard to adjust after all this time. I'm going to try, though, since I want to be as consistent as possible. All right, so this is aspartic acid at a pH of 1. I've got, this is the carboxylic acid group. This is the, with its proton. This is the ammonium group with its proton. Very acidic. All the acidic sites are protonated. There's no charge here, no charge here. The ammonium has its charge. At a pH of 7, this goes away and this goes away. This stays. So we're going to do this. Okay, here we go. And this is what it looks like at a pH of 7. So net charge here is +1. Net charge here, -2 and +1, that's a -1. And then at a pH of 13, this goes away. Remember how we said basic sites at a very high pH lose their proton, they become deprotonated. So if I'm going to draw this one out, it would be carboxylate ion, CH2, carboxylate ion, and then this loses the proton. See, notice this loses its proton. So basic sites only lose again, bottom line, basic sites only get deprotonated at high pH. That's the only time they get deprotonated. Acidic sites are always deprotonated, but they become protonated at a very, very low pH. That's pretty much the summary. All right, so this one you can see has a net charge of -2. All right, there's a term called isoelectric point. What is the isoelectric point? The term isoelectric point is the pH at which the amino acid has a net charge of 0. Now that's easy for all of the neutral, not neutral, for all of the nonpolar side chain and polar neutral. It's somewhere around 7. Your book gives you the exact number. But for the acidic ones, can you see that this is not 0, this is not 0, this is not 0? But you can see, where would it be 0? Somewhere between 1 and 7. Can you see that the isoelectric point has to be somewhere between the pH of 1 and pH of 7? And if you look it up in your book, you'll see where it is. All right? You don't have to memorize any isoelectric points or anything. I just wanted to give you the definition. Okay, good. We'll do some more stuff in the next video.